All right. So, hey everyone, I'm Ramesh. I'll be presenting this paper titled Learning Image Condition Label Space for Multi-Label Classification. I'll be joined by Asfa for the later half of the presentation. So let's get to it. A high-level overview of what this paper is about is it's an architecture which conditions your label space in order to push all your positive labels together and all the negative labels away. In contrast to what of the CNN architectures we've used before, where we directly utilize the output of our CNN to perform the classification. It utilizes the Word2X space in order to capture the label dependencies. Here's like a diagram which sort of summarizes that. So you take an image, you pass it through your ConNet or any pre-trained model that you have. You obtain a transformation matrix. This transformation matrix basically maps your Word2X space into a new space. And in this new space, all of our positive labels will be gathered closer together near the origin, and all of our negative labels will be pushed away from it. So basically, you retrieve all of the labels that are close to the origin as your output. And let's go over some of the existing multi-label architectures that are currently present. So the first one is the deep CNN architectures that all of us are familiar with, the one which FastAI uses. We utilize a pre-trained ImageNet model and we add a couple of layers on top of it and add multiple binary classifiers for each of the multi-label class that we have. So the downside of this approach is that if your labels have some kind of interdependencies, like you have a ship, sea, and then you have boats or things like that, they have like some kind of semantic relationships within each other, but this CNN architecture doesn't capture it. It treats all of them as independent classifiers. So another architecture is the recurrent component to the same model. So what it does is you add another recurrent component to the whole model, which is explicitly present to capture this label dependency. So as you can see in the diagram, you have a ConNet path, and then you have another recurrent path into which you feed the previous label, and you constantly pass the previous output back into it and constantly keep getting labels. The downside of this approach is that it's dependent on the way you order the labels. So depending on how you order them, your results will vary. And this doesn't make a lot of sense because in multi-label setting, the output is like a set. There's no inherent order to it. The other one more architecture is a different loss function, in fact. So the warp loss is something that you can plug into your existing CNN architecture. But what this basically does is that it's a pairwise ranking loss function, which maximizes the distance between positive and negative labels. But there's an additional ranking factor present on it. So what it basically does is before you perform the training step, you rank all of your labels. So like a simple way to think about it is if you have a very over-present label, let's say like you have 1,000 images, out of which 800 images have like ship or something. So the ship will have like a ranking factor of like a very low ranking factor. Whereas if there are certain rare samples like say helicopter or something, which have like just say 50 examples or something, for those the ranking factor will be higher. This way, like when you're performing the training step, your rare classes, even though they occur very rarely, when their images actually come up, the gradients will be higher for them. So that's the gist of the warp loss. Then we have the multi-instance visual semantic embedding architecture, MIE for short. So what this architecture basically does is there's two steps to it. First, you take the image and you run a region proposal algorithm on it, and you extract certain regions from it. For each of these regions, you pass it through a pre-trained convolutional architecture as before, and the output of this architecture goes into the Word2X space. If anyone has any questions, like please stop me and ask. I'm probably going a bit fast. So yeah, so the way this architecture works is you take your region proposals. For each of these region proposals, you don't directly train a classifier on top of it. Instead, you output a word-to-vec embedding, you can say. And the loss function is basically tries to minimize the output of the model, which is a word-to-vec embedding, with all of the other embeddings in your label space. So if your output is actually sun, the 300 dimension sun vector that your model outputs and the true word-to-vec embedding of sun, the distance between those two vectors will be minimized, and the distance between like say clouds or something will be like maximized. Like any of the negative labels will be maximized. Again, this is also a pairwise loss function. And yeah, that's the multi-instance MIE model. So let's try to understand like what our proposed architecture tries to do. So in our proposed architecture, we don't directly utilize the output of the CNN model that we have to perform the classification, similar to the MIE architecture, but we don't directly map our output into the vector space. What we do is instead, we output a transformation matrix. And this transformation matrix is applied to your word-to-vec space, and you project all of your labels into a new space. And in this new, like you can see, basically, like you can like see it from this diagram. So you take the image, you pass it through the coordinate model, you will get a transformation matrix output. And you apply the transformation matrix on the entire like word-to-vec space for each of your labels. Say you have 15 labels, you apply this transformation matrix for those 15 labels, and you'll get a new embedding for all of your 15 labels. And in this new space, all of the positive labels will be clustered together closer to the origin, and all of your negative labels will be projected away from it. Thus, explains the title, which is that the space is conditioned on the image. The word-to-vec space is like sort of conditioned on the image. And this is trained, this is all the loss function for this is also another pairwise loss function. So you have pairs of positive and negative examples, and you try to maximize the distance between both of them. So here's like the CNN component of this whole architecture. You take the image, it's a standard like deep CNN architecture, except in the last layer, you have a fully connected layer, but when you're calculating the loss function, you transform it into a matrix. Well, this matrix is a K by D matrix, where D is the size of your word-to-vec dimensions, and K is the size of your projection matrix, which is the space you see on the right side. And yeah, so you take the image, you pass through the CNN, you get a K by D transformation matrix. So let me explain the loss function a little bit. So this is a small twist on your existing pairwise loss function. So instead of taking every pair of positive and negative labels, what this paper proposes is to take the average of all of your positive labels as one single positive label. This sort of addresses like Ashok's question that he posted on the chat earlier, which is it sort of answers that question, like how does this paper like tackle mislabeled like ground truth examples. So if like in your ground truth data set, if like an image is annotated as a bird and say football might be like a mislabeled example. So in order to reduce the contribution of those mislabeled examples, we perform an average step on all of the positive labels that we have in our ground truth data set. But for the negative examples, we sample like randomly, we just sample from the negative example space. And we try to maximize like the distance between these positive examples and the negative examples. So you can also see the diagram below. So all the blue labels correspond to the positive examples. All the red dots correspond to the negative labels, sorry. So it tries to push away the negative labels and tries to push all the positive labels closer to the origin. And there's also a margin factor, which tries to push the negative labels further away. And yeah, this what we just went through it, maximize the distance between positive and negative labels. It's similar to the triplet loss or the pairwise loss. And the averaging step, which you see here, is done to reduce the contribution of mislabeled ground truth examples. Over to Asfa for the rest of the presentation.
Okay, I think I'm going to keep my webcam off because I'm having a little bit of an unstable network over here. Ramesh, could you stop sharing your screen?
Yeah, I'll do that.
Yeah. So is this visible?
Yes.
Okay, so I'll continue. So we are at model inference. Okay, so at inference time, basically, when an image comes in through the CNN, we get an output as the transformation matrix. So basically what happens is for each label, we have its word embeddings through word2vec. We multiply this with the transformation matrix. So this gives us a representation in k dimensions. I will come to what each stands for, but then basically the k dimensions is your transform space. Okay. Now in the k dimensions, we basically take the L2 norm for each label vector, which is essentially the distance from the origin, and labels which are within a small distance are retrieved. Okay, so this is basically an example to explain the vectorized implementation. Over here, we have the first thing on the left-hand side is your transformation matrix K by D. The next thing is we have our label vectors. Each column vector here represents a label in its word2vec representation. Here, there are 300 dimensions. When you multiply these two, right, you get a transform vector, which is of size k into a number of labels. So basically, the k dimension, each vector column represents your label in k dimensions. Instead of the initial 300 dimensions, we have something in k dimensions. Now, for each of these column vectors, we calculate the distance from the origin. That is, we basically take the L2 norm and return labels which are closest to the origin. Okay, so I think this is a nice summary of what I was trying to explain. Can we move further?
Yes.
Okay. Certain training details which they've described in the paper. So the CNN was first pre-trained on ImageNet before it was trained on the multi-label dataset. The Adam optimization with the momentum was set as 0.9. A learning rate of 1 next 6 was used and was gradually decreased. The word2vec was trained on the Google News dataset with the dimension set as 300. And they basically set their transform dimensions k equal to 100. And data was augmented by mirroring. Okay, so we look at the dataset. It's basically NUS wide dataset. I think the slide covers some basic information. One thing to note over here is that for the papers, the author could only retrieve around 170,000 images. So that accounts for only 63 to 64% of the total images. And they split it in training and test set according to the guidelines. Can we move further?
Yes, please.
Okay.
Just keep going.
Okay, so we'll take a brief look at the metrics. So first we have per class precision and recall. So what we do here is basically calculate precision recall separately for individual classes and then average them out. The other metrics is the overall precision and recall. So here what we have is basically we sum over the number of correctly predicted images for all the labels and divide them by the number of ground truth images in the case of recall. For the case of precision, we divide them by the number of predicted images. Okay, so results. The results are presented. Basically, they take out the top 3 predicted labels per image. As you can see, for this method performs better than WOP and RNN CNN in almost all the metrics. In the case of MIE, the performance is almost similar. But again, all these three classifiers which are discussed here were trained on the full size of the data set, whereas their approach was only trained around 63 to 64% of the data set. Okay. So the next question might be, we are mapping it into a k-dimensional Euclidean space. So how would the performance be impacted if k was varied? So they run an experiment where they vary the range of k from 10 to 100. And what they obtained was the performance remains stable. These two graphs basically trying to explain that there's no appreciable change as the dimensions are increased or decreased. Okay, so we move on to interpretation. According to the authors, one way of looking at this model is a combination of k classifiers which inherit common features from a CNN. So what I mean by that is each dimension in k can be considered a complementary classifier. So to better explain my point, we come back to this matrix again. Here, each column vector represents a label in k dimensions. So what they try to say is that for each row represents a particular dimension in k, which has different values for different labels and can be viewed as an output of a unique classifier. So basically, you can take the top 3 or top 5 predictions per classifier and aggregate the results. Another analysis the authors performed was to investigate how similar are the outputs for the different dimensions in k. And so they took out the top 5 predicted labels and basically use a Jacobian coefficient. So basically, that's an intersection over union. And what they found was the output of the classifiers are very different. So combining these classifiers leads to a powerful committee. Okay, so some extensions and takeaways. One extension which the author briefly talks about is zero-shot learning. What is zero-shot learning? So basically, the model has the ability to predict labels which it has never seen. For example, we can take a model that has been trained to recognize dogs and cats can potentially label it as pet. This is because in the word-to-vec embedding space, dogs, cats, and pets will always occur in similar contexts. Okay, so finally a summary. So what we learn here is that the model learns a transformation rather than a representation. It's simple and compact, doesn't need additional network or layers. It is able to address semantic redundancy and co-occurrence dependency among labels. So basically, this means something like synonyms, and in the case of dogs, cats, and pets. Training is done by utilizing hinge loss, and it has a potential to be extended for zero-shot labeling. Thank you.
Great job, guys. We were looking at another paper called Multimodal Multi-Scale Deep Learning for Large-Scale Image Annotation. That network had an explicit module that was predicting the number of labels. Yeah, this is an interesting problem in multi-label settings where your training data might only have 2 or 3 labels, but based on the threshold you choose to get any sort of predictions, you end up getting too many predictions. Does the current method address this at all, or it's potentially a problem with this approach as well?
So the way this architecture produces, at Inference, right? So once you have the transformation matrix, you apply it on each of the labels, but you only return those labels which are at a fixed distance away from origin. So you can sort of restrict how many labels you get as your output by constricting the distance d from the origin. Does that
I
answer your
see.
question?
I see. Yeah. So maybe at training time, you store some statistic about this distance that you can use then at inference time, something like that.
Yeah, you can basically, like, the way we optimize thresholds by figuring out the optimal threshold to maximize F beta in multi-label setting, right? You can perform a similar step. Once you have a trained model, you can optimize for your value of D, which is the distance from the origin.
Mm-hmm. Yeah, that makes sense. Can you talk a little bit about the why some of the choices from the authors seemed a little bit dated? Like, I think the convolution network they used was an AlexNet. We had already a little bit of a conversation about Ward to Vex limitations. Do you think just swapping out those components for more modern counterparts will actually significantly improve the performance, or were these choices kind of good enough?
Yeah, I think I think they can all be dropped in like as components. I think they can be replaced as such, and probably you can derive better results on it. Even the pairwise ranking loss, I think, can be replaced by utilizing the listwise ranking loss. I was going through it, so I think, like, but the problem still remains is that you will still need like sort of like an ordering for your labels, even if you're using a listwise ranking. But I think that it should still it should still improve the performance regardless. And for word to vec, I think you can probably use a better word representation model, and you can probably derive better performance, ones which can even account for the out of vocabulary words.
Hi there.
Do you guys have any? Oh, sorry, go ahead.
Oh, sorry for that. So similar question regarding the previous one. So you could even replace the linear function, right? So right now the CovNet returns basically a linear mapping, but you could basically return a mini neural net, and then the CovNet outputs the weights for that mini neural net, and that you put the embeddings into that mini neural net so that you can get like more complex functions to get your label probabilities, right?
So are you saying something like, instead of outputting a transformation matrix, you output sort of like like a different neural net into which you pass your word embeddings into it, something like that?
Correct.
I'm not sure like the authors had envisioned something like that.
Ramesh, can I come in?
Yeah, go ahead.
So I think this is one point which the authors mentioned might be looking into as a future work. So they basically say at this point of time, it's just picking up the linear relationships. So what about complex relationships in multi-dimensions?
Yeah, makes sense. Okay.
Do you guys have a good feel for this NUS wide? Flickr datasets are very weakly supervised typically with this tagging approach. I wonder why they didn't measure it on some, more kind of stronger supervised datasets like MS Coco, Pascal VOC, Multilabel. Any comments there? Does the noise level of the data set, significantly hinder their performance here?
So I think based on the way the loss function is designed, it allows you to, so the type of noise that they can handle is the ones where your ground truth in itself is like sort of noisy. Like, instead of having missing labels, if your data has like wrong labels associated with it, then the loss function still performs better. So the Flickr data set, the 81 ground truth labels that were provided, they were like manually verified, and like they are like pretty stable. They're very less noisy. But whereas in the other data sets, I think few of the labels are like missing. Like, so for each class that you have, the number of examples are lesser than what they should be. So I think that is probably the reason why they didn't go for a bigger data set.
And also, do you have any intuition on when some of these other simpler approaches, like the non-continuous outputs, like the softmax output or the kind of one-hot encoded vector approach, like what's the cutoff? Like how many concepts can you model with that before you have to switch to this sort of an embedding approach, continuous representation approach?
Okay, I'm not, I don't have like a good number as such for it, but I think once you have like more than like 100 labels or so, I think it's better to switch to like a embedding space kind of approach. At least that's what I've seen in most of these like what do you call these transformation style approaches that I've seen. Like they all also operate on this Flickr data set itself, and they have proposed these kind of approaches versus using your multiple binary classifiers. And it naturally encapsulates the label dependencies as well. So I think that sort of feels like the go-to approach.
Mm-hmm.
I can actually answer like Sergey's question that he posted on the chat. So he was asking about the average embedding term that was present in the loss. The average embedding is actually calculated per training example. So if you have an image and that has, say, 5 positive examples, and there is a space of like 40 other negative examples, the 5 positive labels that is present for that image, they will be averaged. And the remaining negative labels will be sampled randomly. So you'll do that for each image label. I mean image/label pair that you have. It's not per batch. It's per image. So you'll have to calculate it per image. Each image can have different ground truth positive and negative labels, right? So you'll need to calculate the average positive. What you can say, the average positive term for each image. So it'll vary across images. Yeah, per batch, you'll have to do it per image, you can say. I'll probably like address it a little better.
Hi.
Hey, tell me.
Hey, I have a question. I will do understand using word to vec or any wording in general for this case, because as I see, we are not in any using the quality or semantic nature of that. It's moving the point of the space. The point of having it is that similar content situation and they are in the same, and in the point you're making that the ambient and you're bringing them to a new position, the similar quality or nature of that broken now. So couldn't we have in the first place and move from those positions?
I'm very sorry, I couldn't catch that question. I think my internet connection was dropping off. Would it be possible for you to type your question so that I can try and answer it? Or if someone, if Aswar could catch that question, he could probably answer it.
Sorry, same issues here.
I can answer if you want that.
Could you type out the question?
You want to type it now?
Type it now. Get back to you later.
Long question. Type in the chat.
Have you guys found any actual code for this category of papers? Anyone released their code?
No, I couldn't find any of the implementations, but I think this is a simple enough architecture that we can probably prototype it and try and evaluate the performance on different data sets. I think it should be doable. We couldn't find any.
It would be great to reproduce the paper if we can crawl those images or something pretty comparable.
Yeah, I think that's doable.
Hey, Ashok.
Yep.
Just on your last comment, so I'm definitely thinking about trying it out for the multi-label fluid classification because it very much addresses the problems that I had. In particular, I have like a lot of classes that are overlapping, like carrots, baby carrots, grated carrots, whatever. And it looks like this would be a really good approach to address that issue. Plus, I have like 100 labels to begin with.
Yeah, no, absolutely. I think this is why we want, and we actually have a couple more papers in this family of approaches queued up exactly for this reason. We see a lot of multi-class labels and we see a lot of correlation between labels. So, you know, finding an approach that works pretty well across these different domains would be really valuable for a lot of teams. Okay, we're getting a lot of silence, so maybe we can wrap it up here and continue the conversation on forums. Thank you very much. Great job, guys. Very well presented.
Welcome.
Yeah. Thanks for tuning in, everyone. Yeah, if you have any more questions, post it on the forums. I'll try to answer them.